Every algorithm has its limitations, and hierarchical clustering is no different. In this video, we'll explore some of the drawbacks of this technique, thus the importance of having an alternative. In particular, we'll discuss the alternative being the k-means clustering algorithm. Let's consider the first drawback of hierarchical clustering. Recall that this algorithm requires that we calculate the distance between each pair of data points in our sample. For example, just in step 1 alone, when we have 10 data points, we have 45 pairs of data points, thus must calculate 45 distances. Similarly, to cluster 100 data points, we have to calculate 4,950 distances, and to cluster 1,000 data points, we have to calculate 499,500 distances. And it just goes up and up from here. In short, hierarchical clustering can be computationally expensive. To understand the second drawback, let's revisit the penguin data. The plot at left shows the build depths and lengths for a sample of 50 penguins, and the dendrogram at right displays the hierarchical clustering results based on these two features. Cutting this dendrogram at different heights reveals different clustering results. For example, if we cut the dendrogram at the red dashed line, we split the penguins into 8 clusters. Though the penguins in each cluster do indeed appear to be similar, these 8 clusters also appear to be overly specific. Thus, moving up the dendrogram, we can start combining these clusters, or branches, into bigger clusters, or branches. For example, suppose we split the penguins into 6 clusters. In comparison to the 8-cluster solution, notice that 4 of the clusters remain the same, whereas 2 other pairs of clusters, now represented by the red circles, were fused together. Mainly due to the hierarchical structure of this algorithm, the 8-cluster solution is nested inside the 6-cluster solution. The problem is that, as demonstrated by this 3-cluster solution, when we keep fusing our clusters together, we can end up with somewhat goofy results. Mainly, if we just focus on the data, it seems that the points more naturally cluster into the 3 groups drawn here. Yet, that's not what the algorithm gave us. This goofy example illustrates the greediness of the hierarchical clustering algorithm. It makes the best local decision of which clusters to fuse at each step in the process or dendrogram. And once clusters are fused, they remain fused throughout the dendrogram. They're hierarchical. That is, the only way to get to a 3-cluster solution for the penguins is to step-by-step fuse together pieces of the 8-cluster solution. However, meaningful clusters aren't always hierarchical or nested in this way. For example, the best 4-cluster split might not be fused into the best 3-cluster split, which might not be fused into the best 2-cluster split, and so on. The penguins provided one example of this. Now consider another. Suppose we wish to cluster students based on their responses to a survey covering the courses they've taken, their interests, their residence, and so on. Then the most natural 4-cluster solution might largely cluster students by year in school: first years, sophomore, junior, seniors. And the most natural 3-cluster solution might tend to cluster students into their academic division of their major: humanities and fine arts, social sciences, and natural sciences. But this isn't the solution we'd get. Moving up the dendrogram, the 3-cluster solution has 3 groups: seniors and juniors together, then sophomores, and first years. And these years do not directly correspond to the 3 major divisions. For example, not all sophomores are social science majors. In other words, year in school is not nested in major division. These dynamics are not hierarchical. The main point being, again, that the hierarchical clustering algorithm is greedy. It makes the best local decisions at the bottom of the dendrogram, which, by the time we get to the top of the dendrogram, they don't necessarily produce the most meaningful clusters. Thus, the importance of having an alternative clustering approach. One such alternative is k-means. The general goal of k-means clustering is to split the cases into k non-overlapping homogeneous clusters C1, C2 up to Ck. In order to do so formally, we must have a measure of homogeneity. To this end, the within-cluster variance of each cluster, for example Ck, measures the average squared distance between all pairs of cases within the cluster. For those that like formulas, a formula is provided here. The main idea, though, is that the smaller a cluster's within-cluster variance, the more homogeneous it is. Consider a simple example. Suppose our dataset consists of the 9 cases shown here. Then the best two-cluster solution seems pretty clear. There's a cluster of points at the top left and another at the bottom right. There are also plenty of bad two-cluster solutions, this being just one, and it's quite odd. More mathematically, we can determine that the center clustering solution is good because it produces 2 homogeneous clusters. The cases within these clusters have similar features. Mainly, the average distances between all pairs of cases within the clusters are small. Or, equivalently, they have small within-cluster variances W. In contrast, the clusters at right are not homogeneous. The cases within any one of these clusters have very different features. Or mathematically, the clusters have large average distances between all pairs, hence large within-cluster variances W. Thus, to reiterate, k-means clustering seeks to split cases into k non-overlapping homogeneous clusters C1, C2 up to Ck with small within-cluster variances W. Before writing out the formal algorithm used to achieve this goal, we'll walk through the steps for a theoretical example. Step 0 of the algorithm is to pick the number of clusters k that we want to identify. Now, there's no universal rule or recipe for picking k. Rather, the appropriate values of k are context-dependent. They can be deduced from prior knowledge, data, or even the results of hierarchical clustering. The best thing to do is try out multiple values of k. After all, clustering is a discovery tool. Trying out different numbers of clusters can reveal different important patterns. In our example, we'll play around with using k equals 3 clusters. Throughout the remainder of this example, I'll be posting screenshots from a helpful app built by Naftali Harris. In this picture, the white dots represent the raw data points, their x and y coordinates representing their measurements on 2 features x. With respect to these 2 features, there seem to be 3 distinct clusters of points. And let's see if our 3-cluster k-means algorithm can detect these. And spoiler alert, it will. In order to do anything, we first have to initialize or start the algorithm by picking 3 possible locations for the 3 centroids. We've chosen 3 random and fairly evenly distributed possible centroids here, represented by the dark red, blue, and green dots. Once we've randomly placed these initial centroids, we then assign each case or data point to the nearest centroid. For example, the dots in the blue region at right are nearest to the blue centroid. Thus, they're assigned to the blue cluster. The dots in the green region at the bottom are nearest to the green centroid, thus are assigned to the green cluster. This defines the first set of clusters, and they look quite goofy. For example, the blue cluster is spread out across 2 different locations. But we're not done. In step 2 of the algorithm, we update or calculate new centroids. For example, we check out the red data points that were part of the red cluster and calculate their centroid. Note that if I flip back and forth, these updated centroids are different than the centroids we randomly plunked down in step 1. As such, by shifting the location of the centroids, some of the data points are now closer to the centroids of other clusters. For example, the blue dots at the top of the plot are now closer to the red cluster centroid. Thus, in step 3, we reassign each case to the cluster with the nearest centroid. At this point, it seems that we've successfully identified the red cluster at the top, but we still have some goofy clusters on the bottom. Which brings us to step 4, which is to repeat. That is, we'll iterate between steps 2 and 3 until the clusters stabilize. That is, the cluster centroids don't change much from iteration to iteration. With this, we'll again update centroids for the points assigned to each cluster. Then we reassign the cases to the nearest centroid. Then we update the centroids again. We could keep going, but the results won't change much at this point. Thus, we have our final 3 clusters, and these seem pretty good. After iterating through these steps, we went from 3 random and bad clusters to 3 clusters which are consistent with the 3 groupings in the plot. Before moving on, let's watch a short video of a similar example which puts all of these steps together in one place. In conclusion, the k-means clustering algorithm is summarized here. Really connecting with these ideas requires some practice and play, and that will come next.